Welcome back, Math 30-2. Today we're doing probability lesson 5, which is solving problems using tables and diagrams. So right here we've gone over mutually exclusive and we've done not mutually exclusive. So if we remember that, if it's mutually exclusive in the Venn diagram, there's no overlap. So for mutually exclusive, it would look like this. No overlap, okay, for our sets. Not mutually exclusive, our Venn diagrams would overlap a little bit. I'll make that look a bit nicer. They would just overlap a bit. Okay? So dependent and independent. Well, that's not the same as exclusive and mutually exclusive. For dependent and independent, it matters what happens before if it's dependent. So dependent, probability of B, or in this case, probability B, it matters what happened before. So that would be like picking a deck of cards and picking something like a king, and then the next person picks a 4 and they don't replace it. So it matters. So it's without replacement. Now, independent is with replacement. Another way of looking at mutually exclusive would be kings and queens. They're mutually exclusive. But if I said kings and black cards, kings and queens are mutually exclusive. Kings and black cards are not mutually exclusive because we could have a king that is a black. Half of them will be in the middle. Alright, so here we're going to take a look at our very first question, our very first example, and it just wants us here to fill out this chart first of all. That's what 1A is saying. So we are going to fill out the chart. So we have 350 males in bus B, 200 in car C, and 75 in another. So altogether, how many males are there? There's a total of, we add those all up, we're going to get 625. Now we're going to look at our females. We add these all together. We have, in bus B, we have 300, in car C, or in the car, we have 175, and in other, we have 100. So that's going to give me a total of 575. And we add those all up. Okay? Now we want to know how many are in bus B, or in the bus. So we add these together. I'm going to get 650 are on the bus. How many take a car? Well, we add these together. I'm going to get 375. Now, how many go by any other transportation, which could be walking, something like that? Well, that's going to be a total of 175. Now, if I add these together here, these two, it should equal the same as if I add these three together, which will give me 1,200. So the sum of the top two, these totals, should equal the sum of these totals. Okay? So now, how many students altogether attend the high school? 1,200. So the next question says, use the numbers in the table to determine the probability of it being male. So we want to know, where's the probability of being male? Well, there's 625 males out of 1,000 male students out of 1,200. So that's 625 all out of 1,200, which gives me, if you simplify this, 25 out of 48. Okay, so just plug that into your calculator, then go to math, push fraction, and it'll give you the simplest fraction. So the next one says to determine the probability of a car given that it's male. So we want the probability of a car given that it is male. Okay? So we have to take a look at it. Out of the car, and given that's male, there's 625 total for the male in the car, and there's 200 out of that 625. So we want probability that a male takes the car. Now if we simplify this, I'm going to end up getting 8 out of 25, I believe. Okay? So let's take a look at the next one. The next one is the probability out of all of the males taking a car. Like out of the ones taking a car if they're male. So probability, if they're taking a car, they are male. Because this must happen first. We're looking at the car and they're male. Same thing here. They must be male, and which males are taking a car. Alright? So here, with the probability if first they're taking a car and that they're male. So first is taking a car, because this happens first, and that they're male. So that is going to be 200 out of 375. Alright? So we end up getting that. We simplify it. It's going to give me 8 out of 15. There we go. The next one wants, now do you remember what this sign is for? That intersection is what's in the middle. So it's and. So we want the probability of us being male and taking a car. So male and taking a car, that's only 200. Okay, so probability of them being male and they take a car, that's 200. Well, that's out of everything now. Okay, so that's out of 1200. So that is the same as 1 and 6, I believe. Okay? Now, we're looking at the next part here. It says, if a student selected at random, determine the probability that the student is female. So, at random, if that student is female, we look at this, there are 575 females. So that's out of 5, there's 575 females we could choose from, and there's altogether 1,200. It's 575 over 1,200, which gives me 23, I believe, out of 48. Oh yeah, just look at those. It's also that one above. Should have gone back faster. So, now, travels by bus. So let's take a look at traveling by bus. So, there's 650 out of 1,200. And this will give me 13, if we simplify this, 13 out of 24, I believe. Okay? Now the next one is female and travels by bus. So the last one is female and travels by bus. So it's female and travels by bus. So that's going to be female right here, and travels by bus is 300, and that's all out of 1,200, which is the same as 1 and 4. Okay? So those are done. I'll circle my better answers. Alright, so there we go. Now, C says, identify the following events and determine the probability that a female student travels by bus. So what is the probability that a female student travels by bus? So if we're looking at this, we're looking at a female student and she travels by bus. So altogether, we're looking at a total of 575 to choose from. And we want the probability that she travels by bus. There's only 300 females that travel by bus. Okay? So notice the wording here. The wording is very, very important. So it's a female student that travels by bus. So only looking at female students and travels by bus. So first it's female, then it travels by bus. Okay? So this is saying probability by bus, and it's female. That's another way of writing that out. Okay? That's what that's saying. So we end up getting, I simplify that, I'm going to get 12 over 23. Alright? Now the next one says, a student who drives to school is male. So we want, first of all, we're looking at students who drive. So driving to school, that's going to be the car right here. So driving to school, so that's out of 375. In other words, we're doing student who drives is male. Oops, so that's a car. So that's 375. We're looking at, it's out of 375. And it is male, that's 200. Which gives me 8 out of 15. Okay? So that's how we get that one. Now the very last one here is there are events Are the events the student female and the student travels by bus independent events? So, are the student female and the student travel by bus independent? So we're going to use our formulas from the very beginning again over here. We want to see if they are independent. Okay? So that's saying probability of A and B must be equal to that. So we know the probability of a female and travels by bus is 1 in 4. Okay? We know that part, right? We also know the probability that it being female. So we'll go back to this formula. We're going to say probability of it being female is 575 out of 1200. And we found that right there is 23 out of 48. Bus, so that should be an F. So probability of the female is right. Oh no, is female student travels with bus. Here we go. So probability as female is right there, 23 out of 48. Okay. Notice how when it was and this is a female student travels by bus. So it's given that that happens. This one here is and keywords. So we have 23 out of 48. I'll zoom out here because we're going to be going in and out a bit so we can follow a bit easier. Alright, so then the last one says, and we need the probability of traveling by bus. So what is the probability of going by bus? Is 13 out of 24 as we found out earlier. Now, what we have to do is see if these multiplied together is equal to that, and that will tell us if it is dependent or independent. So we go okay? So we do that because we have P, F, and B must be equal to probability of female multiplied by the probability of a bus. So we continue this off, and I am going to end up getting, I think I could zoom in a bit more for the multiplication, and we're going to end up getting a total of, oh boy, okay? So if I look at this, this isn't quite the same as a quarter, is it? So based off that, when we multiply those together, we know it is not independent. So I'm going to put this right here, not independent. So it's not independent. Okay? And we found that out because it does not satisfy this formula right here. So next question. Next question says, students were given the following problems to solve. The odds that Ava will pass a math this semester is 4 to 1 in favor of the odds that she will pass English this semester are 1 to 9 against. These events are independent. Determine the probability to the nearest hundredth that she will pass. So now we're looking at odds again. So what is the probability that she passes math and English? So first of all, the probability of her passing math is in favor of 4 to 1 odds. So this is 4 and this is against. So if you remember that, that is the same as 4 over 5 to pass math. And English, now we have to multiply. That is going to be, and this is against, so it's really, this is 4, and this is against her. That's 9 to 1 is for her passing, so it is going to be 9 over 10. When we combine that, that's going to give me 36 over 50. Okay? Next one says the probability of her passing math and not English. Well, let's take a look at this. To the nearest determined probability that she, to math and not English, that's going to give me math. The probability of passing math is going to be 4 out of 5. And not English is 1 out of 10, which gives me 4 out of 50, which is the same as 2 out of 25. Okay? Now the last one says math or English. So what is the probability of her passing math or English? Well, or is adding. So that is going to be 4 out of 5 plus 9 out of 10. But now if we add these together, what do we notice? It is way too big. So this will give me over 100. I'm going to get, if I look at this, I'm going to get 17 out of 10. If I add this up, because this is the same as 8 out of 10. That is too big. So as soon as, how can we have over 100%? So now we know that these events are not independent. Okay? These are dependent events. They are not mutually exclusive. These events are independent, but they are not mutually exclusive. Alright? So we have to take a look at this. So we're looking at the same idea, but we're going to look at our formula from before. So that is the probability of math or English, or English, we have the U, union, English, is equal to, because we know these are not mutually exclusive, we have probability of math plus the probability of English, and then we're going to have to subtract the probability of math and English if we look back to our formula. So we continue this, I'm going to end up getting same thing as we had before, 5 over 10, which is, or 4 over 5, which is the same as 8 over 10, plus, now we're going to have 9 over 10, but then we have to subtract 36 over 50 here we got for math and English, which is the same as 18 over 25. Or I'll keep it 36 over 50 because it's easier to make a common denominator. Okay? So if I continue this, these I have to put out of 50, so I'm going to get 40 out of 50 plus 45 out of 50, and then I'm going to minus 36 out of 50. Okay, so I combine these, I am going to end up getting 40 plus 9, which is 49 out of 50. So that is my probability of doing that. I kind of did A and B all there together. Now the other way we could do it is by doing a tree diagram. So I'll zoom out so we can see the tree diagram. So the other way we could do it is by doing a tree diagram. Now, other students choose to take the probability and solve using a tree diagram. So if we look at it this way, they did probability of math, of passing math, and then notice the dash there, there's a little tiny tick there, that's not passing math is 0.2. So passing English, and then if we pass math, we may pass English or not pass English. So this is 0.1. Then right here, passing English again is 0.9, and not passing English is 0.1. Okay? So if we continue this, we end up getting, for this one, is the probability of M and not E, and that little tick from what we learned before, that's not, is equal to 0.8 multiplied by 0.1, which is equal to 8%. Okay? So the probability of here is probability of not math and English, of not passing math but passing English is equal to 0.2 multiplied by 0.9, which will give me 0.18, or the same as 18%. And the last one is the probability of not passing either, which will be equal to 0.02, or 2%. Okay? We'll multiply those together. Alright? So after that, we could answer all the rest here. So it says the probability, this is in probability, is 72%. So I is 72%. We're just answering back this question here. Math and not English. Well, math and not English is 8%. Which is actually the same as 2 out of 25. And the last one is math or English. Well, passing math or English is all of them except for this one here, which is going to give me 98%, okay, or 0.98, which is actually the same as that there. This way may seem easier, but this way is a lot faster and efficient once you get going. Because if you have a very complex tree diagram, this one can be very difficult. So now we're looking at example 3. So it says, in a game of field hockey, I'll just move this up a bit, and adjust. So here we go. In a game of field hockey, the probability that the Dinos score a goal from anywhere, from any short corner is 1 in 8. During the first half of the match, they are awarded 2 penalty corners. Use the probability tree diagram to determine the probability of these 2 corners. So we have the first one is probability of goal, and then probability of not a goal. And then here we have probability of goal, not a goal. We can either score or not score, right? I just said goal or not goal. Okay, the dash represents the not. So what is the probability of getting 2 goals? That's only going this way. So the probability from a short corner, this is 1 in 8. This here is 1 in 8. Okay? The probability of not getting it must be 7 and 8. So this here is 7 and 8, 7 and 8 every time it says not, and 1 and 8 every time it says 4. So I continue this. This is the same as probability of goal, and goal is equal to 1 over 8 multiplied by 1 over 8, which is the same as 1 over 64. Alright? Now the next one is, we look at this one, probability of goal and not a goal is equal to 1 over 8 multiplied by 7 over 8, which gives me 7 over 64. And now we're going to do one more. Probability of 1 goal. So probability of, this is a not a goal and a goal is, well, it's going to actually be the same as this because it's 7 and 8 and 1 and 8, 7 over 64. And the last one is probability of not a goal and also not a goal, which is 7 and 8 and then 7 and 8, which will give me the probability of 49 over 64. So these are my 3 probabilities. So the next part says 2 goals. What is the probability of 2 goals? That is this one right here. This is the only one where they both score, and that is 1 in 64. Next one says 1 goal. Well, I could have, here's one with 1 goal, and here's one with 1 goal. That's 7 in 64 and 7 in 64. So I have to add these together. It's going to give me 14 out of 64. And the last one is at least 1 goal. So at least 1 goal, I could have 2 goals, or I could have 1 goal. So I have to add the 2 goals and the 2 1 goals together. So that's going to give me these two, the 2 answers I had before, this one and this one. We add them together. That's going to give me 15 out of 64. And the last one is no goals. Well, that is 49 out of 64. This is the only way of getting no goals, is if you miss and miss. Okay? So now we are going to look at the probability tree for dependent events. So the first one here is two machines, A1 and A2, produce all the glass bottles made in a factory. The percentages of broken bottles produced by these machines is 5% and 8% respectively. Machine A produces 60% of the output. I'll just zoom in a little bit more so we can read. So, there we go. So now, the first part says, first introduce symbols to the thing. So we have PA is machine A. They're kind of giving a step-by-step basis on how to do this. So we have machine A is PA1. So what is the probability bottle is from machine A? So the probability first that the bottle is from machine A is, well, it is 60%. So that's 0.6. All right? So then the probability that it comes from machine B is 0.4. Now we're looking at it, it's only 5% that bottles are broken. Okay, so this is saying it's 5% chance that the bottles come from machine A are broken. So that is probability that's coming from machine A that they are broken. That they're broken from machine A. Okay? Oh, A1. And then the probability is 8%. That is, they're coming first from machine B and they're broken. Okay? So from machine B, they're broken. They can't be broken and then from machine A because they break first in the machine. So which machine are they from? And that they're broken. So the next part is to set up a tree diagram. So one person here sets up a tree diagram. So they have the probability of B and A is 0, and we have these already made before, 0.05. So that's broken and it comes from machine 1. Okay, so here is that's broken, or that it's not broken and it comes from machine 1 is 0.95. Okay, and now let's take a look at it. So here we go. So these are dependent because it depends on which machine it comes from. If it's from machine A, there's a less chance of it being broken. If it comes from machine B, there's more of a chance. That's why it's dependent. The broken bottles are dependent which machine they come from. So we have PA and PB is equal to probability of A multiplied by the probability of the broken bottles not being A. So this is the same as 0.6 multiplied by 0.05. So the probability that they come broken from this machine is actually, if they're broken and from A, is very small. It is only 0.03. So that is 3% chance that they come broken from this machine. The next one is saying that it's broken from machine A, or that it's not broken and from machine A. So that probability that's not broken and from machine A. So that is 0.6 multiplied by 0.95. Well, if we multiply these together, I'm going to end up getting 0.57. Alright? So that is my answer for this one. So that is the probability that it is not broken and from machine A. If we're taking a bottle, any bottle, it's not broken and from machine A. So now we're looking at the probability for going to the second machine, A2. That is 0.4. Now the probability that's broken in machine 2 is probability is equal to probability of of it being broken, and in machine 2 is equal to 0.08. Now the probability of it not being broken and in machine 2 is equal to, well, it's the complement of it being broken, which is equal to 0.92. So now the first one here, we want, this here is, we have it from A2 and it's not broken. So it's coming from A2 and it's not broken. So that is probability of machine 2 and it is not broken. Well, that will give me 0.4 multiplied by 0.08. Because notice the probabilities for them broken are different from each machine. This ends up getting me 0.032. Okay, so that's the probability. So it's around 3%. Slightly more than this one, it's just a little bit more. Now the probability that it's not broken and from machine A, well, that is going to be probability that it is not broken and it's from machine A. So from machine A and it's not broken is, notice the order here, I have it's from this machine and not broken. So then it's from that machine and it's not broken. So this happens first, then that, right? So it's from that machine, and it's not broken is 0. Now what is it? 4 multiplied by 0.92, which gives me a total of 0.36%. Or 0.368, not percent, so 37%. Okay? That's that one. So, next part is, Cheryl asked John the question at random. Determine the probability that is broken bottle by machine A. So basically, ask them at random, probability is broken from machine A, that's probability of A from machine A1, and it's not broken, and it's broken is only equal to 0.03. Another words of doing it is you could have just taken these and multiplied those together without the tree there. So then the next one says, which of the final outcomes in the diagram related to the event of a bottle is not broken? So which of the final of the bottle is not broken? Okay, so pretty much we could have it coming from this machine and not being broken, or this machine and not be broken. So it is this outcome here or this outcome here. So we have two outcomes. So that is the same as P we could have from machine 1 and not broken, or we could have probability from machine B, or coming from the second machine, and not broken. Which is the same as, if we say or, that means we must add, so that is 0.57 plus 0.36, okay? So we add these two together, so that's all right? So what is the probability that the bottle is not broken? This is continuation of that. We add those two numbers together. I'm going to get 0.938. Okay? There we go. Last example before your assignment. And just go a bit more right there. So, as part of an experiment into the learning process, a mouse is put into a maze and rewarded with food every time it turns right. If the mouse turns right, the probability that it turns right the next time is increased by 20%. If the mouse turns left, the probability that it turns left the next time is decreased by 20%. Assume that there is an equal probability that the first turn will be left or right. So, now here is an example of a dependent event. Why? Because if the mouse turns right, the probability that it turns right again increases. If it turns left, the probability that it turns left again decreases, and turns right again increases. So it really matters on what happened first or second. Okay? So, in this case, let R and L1 represent the events. So, what is meant by R2/R1? So that what is meant by this? This is saying that it turns right the second time, right the second time, given that it turned right the first time. All right? So determine the exact decimal and probability of each event. So this one's saying the first turn is right. So it wants us to determine the probability that the first turn is right. Well, in the first turn, it can either go left or right. It doesn't know that it's going to get food for which turn, so it is only 0.5. Okay? The first turn is to the left now. Well, same idea. It could either turn left or right. It's the complement of turning right, so that's 0.5. There is no previous knowledge. So the second turn is right, given that the first turn is right. So the second turn is right, given that the first turn is right. So the second turn is right, so that is 0.5 plus, because it's the probability of the first term, plus 20%. Oh, I'll zoom out here so we could see this. It's the probability of the first turn, right, plus 20%. It's going to increase, because if it turns right, it'll get a reward, so it's increased. So it's probability of the first term plus 20% of 0.5. So it has or 20% of 0.5, it has a 20% increase of 0.5. So that will end up giving me which is equal to 0.6, 60% chance. So the second turn is right. So the second turn is 60% chance, 60%, because it's a 20% increase of probability. I can't just add 20%, because if I do it 3 times, how can it 3 times? That's an increase of 60%. How can it be 100%, 110% chance of going right? So that's why we have to take its 20% chance of the original probability. Okay? So in other words, we'll look at it later with the probability, the terminology. So the second turn is to the left, given that the first turn is to the left. So the second turn to the left, well, that's a 50% chance, right? Now, it says it decreases the probability of turning to the left if it turns left. So that's minus 0.2 multiplied by 0.5. So 20% of the first turn, which is equal to 0.5 minus 0.1, which is 40%, which is 0.4. Okay? So now the second part here says, put the probabilities of B into probability tree diagram, complete the diagram, use the diagram to determine the probability of the first term sums. So the next part here is I'm going to let you guys do that, is you're going to put this into a tree diagram and do that with yourself. Okay? So good luck on the assignment, and I will see you tomorrow.